Hello everyone, a very good evening to all. Myself, Vivekananda Naik. I am a PhD research scholar in the Department of Energy Science and Engineering, IIT Delhi. So, I am the PMRF TA of this NPTEL course, Atomic and Molecular Physics, which is being flowed this January 2026 session with course code NOC 26PH18. I will be taking weekly interaction sessions, which will occur each Monday from 7 p.m. to 9 p.m., where I will be solving a few sample problems that are based on the week's lecture content or course content of the course Atomic and Molecular Physics. So, if you talk about the problems that we are solving last week, last Monday, we solved problems related to the Faraday's law of electrolysis, where we solved a few sample problems. Now you will be solving a few problems that are based on the Millikan's oil drop experiment. But before that, let's discuss a few things about this week's lecture. So, week 2, in week 2 course, it was mainly related to structure of a atom, and the structure of atom was given by different scientists, or the model of atom was explained by different scientists. So this week's lecture was mainly structure of atoms. So initial the most empirical model is given by Dalton's. Then Thomson came. So Thomson's model was the first atomic model given by J.J. Thomson in 1907, where there were a few drawbacks, like he was not able to explain the nature of hydrogen spectra. Like hydrogen spectra, as we know, there are different series of lines in hydrogen spectra, and each series contains another number of lines, which Thomson model could not explain. Then also Rutherford, he gave a model in 1911, where through we all know, through alpha particle scattering experiment using a gold foil, Rutherford discovered the nucleus, and Rutherford gave atomic models. But Rutherford was unable to explain the stability of the atom. Like when we all know, the electrons, when they are revolving around the nucleus in a circular orbit, they will continuously lose energy, and they will eventually come closer to the nucleus, and atom as a whole will collapse. But this was not again explained by Rutherford. And also the atomic spectra, again the hydrogen spectra, was also not fully explained by Rutherford. Then came Bohr, and Bohr's model was, as you can say, up to most of the properties of the atom was explained using Bohr's model. A few of the things that were not explained was explained with the help of Sommerfeld's modification to Bohr's atomic model, and the Bohr's atomic model is given given in 1913. So we will discuss a few problems that will be based on Bohr's atomic model. Like there is, we know Bohr's model of hydrogen atom has given. So plus Z is the charge of the nucleus, and then E was electron which was revolving around the nucleus, and R was the radius of the orbit. Then the derivations were also performed in this week's lecture to derive the expression for Rn, Vn, and energy of the nth orbit. Uh, so all these things that we will discuss, cover in the problem that we will be solving. So mainly, if you talk about Bohr's model, there are mainly two things. So one was the orbits were stationary orbit, stationary orbits, that is the energy is fixed. So as long as an electron is revolving in an orbit, its energy remains fixed. So that was one of the important postulates of Bohr's atomic model. Then Bohr also gave postulates related to the quantization of angular momentum. Quantization of angular momentum, which says angular momentum we know mvr is equals to nh cross or 2 pi, where n is 1, 2, 3. So the angular momentum of an electron in an orbit is quantized. Then, so since the orbits were stationary, so when as long as the electron is revolving in an orbit, its energy remains same. But when it gains energy or emits energy, then transition occurs from one energy level to another energy level, and the energy of the radiation is given by h nu, and the difference between which is given by the difference between the two energy of the two energy levels, that is E1 minus E2. So then also if you start deriving the hydrogen the Bohr's model of hydrogen atom, then we will what we can say, we can balance the centripetal force with the electrostatic force of attraction, which was not explained by Rutherford. There are some issues with the stability, how to explain the stability of the atom. So, but Bohr explained that. So when the electron is revolving in an orbit of the radius r, so the the centripetal force is equals to electrostatic force. So centripetal force we all know. Centripetal force is given by mv square by r. And electrostatic force is k z e square by r square. So by balancing these two forces, we can derive the expression for radius, velocity, and energy of the hydrogen atom. So before that, let's solve a few problems that related to Millikan's oil drop experiment. So the question says, in Millikan's oil drop experiment, an oil drop of mass 9.8 into 10 to the power minus 13 kg is balanced by applying a potential difference of 19.6 kilovolt between the two plates, which are 6.4 millimeter apart. Calculate the number of elementary charges on the drop, where it is mentioned that we can take g equals to 10 meter per second square, and value of elementary charge is 1.6 into 10 to the power minus 19 coulomb. The options are option A 4, option B 10, option C 20, or option D 40. So this is related to Millikan's oil drop experiment. So what is Millikan's oil drop experiment? So through Millikan's oil drop experiment, it was concluded that the electric charge is quantized, like it is multiple of charge of an electron. So basically we discovered the charge of an electron, and that again led to the concept that electrical charge is quantized. So how the experiment works? So here the question says an oil drop of mass 9.8 into 10 to the power minus 13 kg is balanced by applying a potential difference of 19.6 kV. So we know if we drop an oil drop, so it will fall. Suppose the mass of the oil drop is m. So what will be the weight of the oil drop? So due to the mass m, the weight will be mg, which will be acting downwards. Now the question says it is balanced by applying a potential difference of 19.6 kilovolt. So it is balanced by a potential difference of 19.6 kilovolt. Suppose it is balanced by a potential difference between two plates. Suppose these are the two plates. Suppose this is plate A, this is plate B. Now this is balanced. That means its velocity is zero. It is not changing. It is not moving. So it is getting balanced by another force, and that force is due to the potential difference applied between the two plates. So this is the two plate, and the separation between the two plate, it is given 6.4 millimeter. And what is the potential difference applied between the two plates? The potential difference is 19.6 kV. So 19.6 kilovolt of potential difference applied across the two plates, which are 6.4 millimeter apart. Now we need to find out the number of elementary charges on the drop. So now if the charge of the oil drop is Q in an since the potential is applied between the two plates, there will be an electric field which is acting two plates. So since the oil drop is getting balanced, so the weight mg which is acting downwards, it is getting balanced by some force which is acting upwards, and this upward force is due to the electric field. The force due to the electric field, because so what is the force? It is q into e. So what we can say, we can write the weight. So when the oil drop is balanced, then we can say mg equals to qe. So we can say, so again e, we know e is equals to v by d. So we can write mg equals to q v by d. Then what is the value of charge? So charge q will be mg d by v. So this is the expression required for calculating the number of elementary charges on the oil drop. So we know the values. M, we know M is, it is given in the question, it is 9.8 into minus 13 kg. 9.8 into 10 to the power minus 13 kg. Then V is also given. V is 19.6 into 10 to the power 3 volt, because it is given in kilovolt, and the distance between the two plate is 6.4 mm. So 6.4 into 10 to the power minus 3 meters. So everything should be in same unit. So I am writing all in SI unit so that we can calculate the value. So the question says calculate the number of elementary charges. So the charge of one elementary charge, that is the charge of electron, it is given as 1.6 into 10 to the power minus 19 coulomb. So if you put all the values, so it will be how much? It will be 9.8 into 10 to the power minus 13 into 10 meter per second square, the value of g. Then d is 6.4 into 10 to the power minus 3 divided by v. V is 19.6 into 10 to the power 3. So if you calculate 9.8 to, then it will be 6.4. So 6.4 is 3.2. So it will be 91.6, not 19. 19.6 into 3. So this is Q. Q is Ne. So Ne is how much? 3.2 into 10 to the power. So 32, T will be 32 into 10 to the power minus 19. That implies N will be 32 into 10 to the power minus 19 divided by 1.6 into 10 to the power minus 19. So if you, it will be 20. So N will be 20. So the number of elementary charges on the drop is 20. So option C is the correct option. I hope this is clear to you. Now we'll move to now we'll move to question number next question. Again, it is based on Millikan's oil drop method. So it says in Millikan's oil drop experiment, a charged oil drop of mass 3.2 into 10 to the minus 10 kg is held stationary between parallel plates 6 mm apart by applying a potential difference of 4800 volt between them. Then how many electrons are there in the oil drop? So it is pretty much similar to the previous question. Again, we know mg equals to QE, or you can say mg equals to ne, and E is V by D. So N is mg D by NV. If you put the values, we know N is mg, m is 3.2 into 10 to the power minus 13 into G is 10. It is 6 mm apart, so it is 6 into 10 to the power minus 3 divided by EV. So E is 1.6 into 10 to the power minus 19 into V. V is 4800. So if you calculate, it will come out to be 40 into 10 to the power minus 19 coulomb divided by 1.6 into 10 to the power minus 19 coulomb. So N will be 25. So the correct answer is option B, that is 25. So these two questions are pretty much similar. Now move to another question based on Millikan's oil drop experiment. So again, the question says the mass of the oil drop is 6.4 into 10 to the power 14, and it carries a charge of 8 into 10 to the power minus 19, and it remains stationary between the two plates separated by a distance of 5 mm. The voltage that must be applied between the two plates, and the options are option A 3920 volt, option B 4210 volt, option C 2375 volt, and option D 1800 volt. So again, the formula is same, but the unknown quantity is different in this question. So mg equals to QE, mg equals to NEV by D, and here we don't need to put Q equals to NE, we don't need to expand because Q is already given, which is 8 into 10 to the power minus 19 coulomb. So we can directly write is equals to Q V by D, and you need to find out V. So V is mg D by Q. So V is m. What is the value of m? M is 6.4 into 10 to the power minus 14. 6.4 into 10 to the power minus 14 into G. In the question it is mentioned G is 9.8, so we will take 9.8 into D is 5 mm, so 5 into 10 to the power minus 3 divided by the charge is 8 into 10 to the power minus 19. So if you write To solve it, it will be coming around. So it will be 6.4 into 9.8 into 5 divided by 8 into 10 to the minus 14, 10 to the minus 3. This is minus 17 plus 19. So it will be 100. If you, so this is, if you got with 1.6, this will be 5, this will be 4, 5 gets cancelled out. 9.8 into 4, 9.8 into 4 is 39.2 into 100, which is 3920 volt. So the voltage applied is 3.92 kilovolt or 3920 volt. So the correct option is option A, 3920 volt. I hope this is clear to you. Now we'll move to question number 2. Question number 2 is based on Bohr's model of hydrogen atom. So it says, in the Bohr's hydrogen atom model, the radius of the stationary orbit is directly proportional to n equals to principal quantum number, is directly proportional to n or n square or n cube or n to the power half. So this question is based on Bohr's model of hydrogen atom. So what will be the, so first we need to find out the expression for R, and from that expression we can see the dependency of R on n. So either it is proportional to n or it is proportional to n square, n cube or n to the power half, that we will figure out. So I'll give you a few minutes and then we will discuss. So we know, like I was discussing about Bohr's model of hydrogen atom at the beginning of the today's interaction session. The Bohr's model of hydrogen atom, the derivation is based on balancing the two forces, that is centripetal force and electrostatic force. So the centripetal force is mv square by r, and the electrostatic force is k e square by r square. Again, we can write mv square by r equals to k is 1 by 4 pi epsilon 0 e square by r square. Again, from Bohr's postulates, we know angular momentum is quantized. So mvr is equals to nh by 2 pi. That implies v equals to nh divided by 2 pi mr. So if you put the value of v, so here if you can see, we can so 1 r gets cancelled out. So m v square is equals to 1 by 4 pi epsilon 0 e square by r. So if you put the value of v here, m v is nh divided by 2 pi mr square is equals to 1 by 4 pi epsilon 0 e square by r. So if you solve it, what you will get? You will get r equals to n square h, because r is on this side. So r will get 1 r will get cancelled out here. So this r will come to the numerator of this side. So r will be proportional to n square. So n square h square epsilon 0 divided by pi m jd square. So this is the expression for r, where we can say it is proportional to n square. And if you put all the values, because we know the value of h epsilon 0 pi m for hydrogen, z is 1 for hydrogen, and e we also know. So for hydrogen atom, r1, which is called as Bohr's radius, it is 0.529 angstrom. That is the distance of the first orbit. So this is n equals to 1, this is r1 or r0, or we can say a0. A0 is called as the Bohr's orbit. So the correct option is option B. It is proportional to n square. So Rn is proportional to n square for a constant z. I hope this is clear to everyone. Now we'll move to question number. Sorry, 8 minutes. So now we'll move to question number 3. So question number 3 says, some transitions of hydrogen atoms are shown in the above figure. Identify the transitions corresponding to the preferred series. Options are option A, B and C, option B, D and E, option C, F, or option D, G. So it is related to the spectra of hydrogen atom, and we know for hydrogen atom, hydrogen spectra contains a number of series, different series depending upon the value of principal quantum number, that is n, when the transition occurs. So if you discuss about hydrogen spectra, so suppose this is infinite as mentioned here. So we'll draw. So again, if you remember, sorry. So since we'll be solving a few questions based on the energy, so let's not discuss about that. But let's only we all know the energy levels are not equally spaced. So Suppose this is n equals to 1, this is n equals to 2, n equal to 3 will be closer to n equal to 2 than n equal to 1 and n equal to 2. So it will be n equal to 2, n equal to 3, then 4 will be even more closer, 5 will be even more closer, n equal to 6, n equal to 7. So this is n equals to infinite. So now hydrogen spectra has different series according to the transition. So when the transition occurs from n equal to 2, 3, 4, 5 or n equal to greater than 1 to n equal to 1. Suppose the transition is occurring from n equal to 2 to 1, n equal to 3 to 1, n equal to 4 to 1. This is called as Lyman series. Similarly, when the transition occurs from higher orbits to n equal to 2, this is called as Balmer series. Then for n equal to 3, Lyman, Balmer, Paschen. Then for n equal to 4, it is bracket. For n equal to 5, it is Pfund. So when the transition occurs from higher orbits to n equal to 1, this is Lyman series. Then for n equal to 2, Balmer. For n equal to 3, Paschen. N equal to 4, bracket. N equal to 5, Pfund. Now let's see the question. So in our question, it says identify the transition corresponding to Pfund series. Pfund series means n will be 5 Lyman, Balmer, Paschen, bracket, Pfund. So n equal to 5. So now we need to find out the transition which occurs from higher orbit to n equal to 5. So now see, so from n equal to 1, this is A, F and H. So A, F and H, this corresponds to Lyman. Then for n equal to 2, D, sorry. So D is Balmer. Then for n equal to 3, B, C and E, B, C and E, this is Paschen. Then n equal to 4, there are no transition that is occurring from higher orbit to n equal to 4. So then n equal to 5, n equal to 5 is G. So G is n equal to 5, which corresponds to Pfund. So this transition, this is n equal to 5 and this is n equal to infinity. So higher n from any higher orbit to n equal to 5. So the transition in, so the G transition corresponds to the Pfund series of hydrogen spectra. I hope this is clear to everyone. Now we will move to question number 4. Question number 4 says, which of the following is true? Lyman series is a continuous spectrum. Option B, Paschen series is a line spectrum in the infrared. Option C, Balmer series is a line spectrum in the ultraviolet. Or option D, the spectral series formula can be derived from the Rutherford's model of hydrogen atom. So we have to analyze this 4 sentence and we need to find out which of the following sentence is true. So Lyman series is a continuous spectrum, Paschen series corresponds to infrared, Balmer series corresponds to ultraviolet, or the spectral series formula can be derived from the Rutherford's model of hydrogen atom. So I'll give you a few minutes and then we will analyze it to find out the true option. So now let's discuss about the energy values. Then we can solve this question, because the spectra, depending upon their energy, they correspond to different uh, segment of the electromagnetic spectrum. So it will come into the picture. But let's first discuss option A. So option A says Lyman series is a continuous spectrum. We know in Lyman series it is not continuous; it has a number of lines. So we can say Lyman series is a line spectrum. It is not a continuous spectrum. So not only Lyman series, all hydrogen spectra or series are line spectra. So Lyman series is a line spectra. Then Paschen series is a line spectrum. Like here also you can say it is written as line spectrum. So Paschen series is a line spectrum in the infrared region. Barmer series is a line spectrum in the ultraviolet region. So now let's talk about different series of the hydrogen spectra. So now if you talk about the lines, so this is Lyman, Balmer, Paschen, bracket, and Pfund. Lyman, Balmer, Paschen, bracket, and Pfund. So now we know for Lyman series the transition occurs from higher orbit to n equal to 1, and for Balmer it is n equal to 2, then n equal to 3, n equal to 4, like that. So it is n equal to 1, n equal to 2, n equal to 3, n equal to 4, n equal to 5. Now you see here we do the energy levels. So the gap between n equal to 2 and n equal to 1 is maximum. So this gap is maximum. Then as we go towards the higher energy value, higher energy levels, the gap reduces. So depending upon this, so this the gap reduces. So the energy values correspond to the spectra. It also changes. So depending upon that, the series is arranged into different spectrum. So if you talk about Lyman series, it corresponds to ultraviolet region. Balmer series corresponds to visible region. That's why H alpha H beta line you must be you must have heard of H alpha H beta line. That is the first line of Balmer series and second line of Balmer series. They are in visible region, so we can see them using an optical emission spectroscopy. So it is emission spectra. It is not absorption spectra. It is hydrogen emission spectra. So the emitted light, the energy of the emitted light corresponds to difference between the two energy levels. So the involvement of lower energy level leads to higher energy. So as we go on higher n values, the energy changes. So that's why Lyman corresponds to ultraviolet, Balmer corresponds to visible, Pasten corresponds to infrared, and all these Bastian, bracket, and Pfund they corresponds to infrared. So this is the energy value. So energy increases in this way, and the frequency increases in this way. Sorry, the wavelength. So since energy increases in this way, so the wavelength increases in a so the wavelength of infrared region is higher as compared to ultraviolet region, but the frequency of ultraviolet region is higher when compared to infrared region. So here you can see it is mentioned that Paschen series is a line spectrum in infrared. So Paschen series is a line spectrum in infrared, so it is correct. Balmer series is a line spectrum in ultraviolet. No, it is not correct. Balmer series is a line spectrum corresponds to visible region. So this is also not correct. This is not correct. And option D, the spectral series formula can be derived from the Rutherford's model of hydrogen atom. We know Rutherford's model of hydrogen atom did not give any explanation related to the hydrogen atomic spectra. The hydrogen atomic spectra was derived from Bohr's model. So hydrogen spectra was derived from Bohr's model. So Again, this is not correct. So the correct option is option B. Paschen series is a line spectrum in the infrared region. I hope this explains the four options, and the correct option is option B. Now question number 5. Question number 5 says the energy required to knock out the electron, that is to make the electron completely free from the attraction of the nucleus in the fifth orbit of a hydrogen atom is equals to option A 13.6 electron volt, option B 1.5 electron volt, option C 0.544 electron volt, or option D none of these. So question says what is the energy required to knock out the electron, that is to make the electron completely free from the attraction of the nucleus in the fifth orbit of the hydrogen atom. In the fifth orbit means n equals to 5. So we need to first calculate the energy value of the fifth orbit of hydrogen atom, and then we can say what will be the required energy to knock out the electron from that orbit. So I'll give you a few minutes and then we will discuss. So we know from the energy expression, the energy of an nth orbit is given by minus 1 by 8 m z square e fourth divided by n square h square epsilon 0 square. If you put all the values for hydrogen atom, it will come out to minus 13.6 divided by n square in electron volt. So for fifth orbit, n equal to 5, for fifth orbit. So what will be the value of energy of fifth orbit? E5 will be minus 13.6 divided by 5 square, which comes out to be minus 0.544 electron volt. So now if you see the options, options are all positive: 13.6, 1.51, 0.544, or none of the above. So will the correct answer will be none of the above? No. The correct answer will be option C, 0.544 eV. But how it is positive? Because this E5 is the energy of the electrons energy. So this is the energy of the electron, that is the energy an electron have when it is present in the fifth orbit of the hydrogen atom. But we need to find out the energy required to knock the electron out of the nucleus, that is completely free. So this is, suppose this is E I, this is the initial energy, minus 0.544 ev, and we need to make the electron free so that the final energy of electron will be 0 ev. So if the energy of the electron is minus 0.544, how much amount of energy required to make the energy of the electron at 0? So the required energy value will be E required will be E final minus E initial, will be 0 minus of minus 0.544, which is 0.544 ev. So the amount of energy required to knock the electron out of the fifth orbit is 0.544 ev, which is the opposite of the electron energy, minus 0.54 ev. Why the energy is negative? Because the electron is bound to the nucleus. That's why the energy is negative. So in order to make the electron free, we need to supply the same amount of energy, so the energy will be 0. I hope this clears the this is clear to everyone. Now we'll move to question number 6. Question number 6 says, if the wavelength of the first line of the Balmer series of hydrogen is 6561 Armstrong, then the wavelength of the second line of this series would be. So we know for Balmer series, what is the expression for Balmer series? So when the transition occurs from higher orbit to n equal to 2, the emitted radiation corresponds to Balmer series. And if you talk about the expression for wavelength, it will be 1 by lambda equals to R 1 by n1 square minus 1 by n2 square, where R is the Rydberg's constant, 1.097 into 10 to the power 7 meter inverse. So for Balmer series, n1 equals to 2 and n2 is 3, 4, 5, like that. So what is the first line of Balmer series? So for first line, n1 will be 2 and n2 will be 3. So first line of Balmer series, what will be the value of the wavelength? 1 by lambda will be R 1 by 2 square minus 1 by 3 square. So R 1 by 4 minus 1 by 9. This is R 9 minus 4 by 9 into 4. So it is R equals, sorry, R into 5 by 36. So 1 by lambda is 5 R by 36. That implies lambda is 36 divided by 5 R. Now the question says, if the first line is 6561 Armstrong, what is the wavelength of the second line of the series? So for second line, N1 is 2 and N2 is 3. Sorry, N2 is 4. So it will be 1 by lambda 2. It will be R 1 by 2 square minus 1 by 4 square. So it will be R 1 by 4 minus 1 by 16. It will be R 16, 16 minus, sorry, 4 minus 4 minus 3. So it will be, sorry, 4 minus 1. It will be 3R by 16. So 1 by lambda 2 is 3R by 16. That implies lambda 2 is 16 by 3R. So let me add another slide. So what is lambda 2 by lambda 1? So lambda 2 by lambda 1 is equals to 16 by 3R into 5R by 36. So R gets cancelled out. So it is 20 by 27. So what is lambda 2? So lambda 2 is 20 by 27 into lambda 1. So 20 by 27 into lambda 1, it was given 6561 Armstrong. So it will be coming out 4860 Armstrong. So the second line of Balmer series will be 4860 Armstrong. So the correct option will be option D, 4860 Armstrong. I hope this is clear to everyone. Now I'll move to question number 7. Question number 7 says, the spectral series of the hydrogen spectrum that lies in the ultraviolet region is the Balmer series, Preferred series, Paschen series and Lyman series. We have already discussed. Lyman series corresponds to ultraviolet, Balmer series corresponds to visible, Paschen series corresponds to infrared and Preferred series corresponds to infrared. So the series corresponding to ultraviolet region is Lyman series. Again, because the energy involvement is higher because it involves n equal to 1 level to other higher level. So the energy difference is more for n equal to 1 to n equal to 2. And again, if you go to higher levels, again the energy difference will be more. Like from n equal to 3 to n equal to 1, the energy of the radiation will be even more than n equal to 2 to n equal to 1. So Lyman series corresponds to ultraviolet region. Now question number 8. Question number 8 says, the ratio of the wavelengths of first line of Lyman series and first line of Balmer series is? Options are option A 1 is to 3, option B 5 is to 27, option C 9 is to 25, or option D 4 is to 9. So again, this question is similar to the previous question that we solved, where the wavelength of first series was given and the wavelength of second series was needed to be calculated. But here, in that case, it was of same series, but here it is of different series, but the approach will be same. We will calculate the first line and second line in terms of Rydberg constant R, and then we will calculate the ratio of the wavelengths of the two line. So with this, I will be giving a few minutes to try to solve this question, and then we will discuss. So let's solve it. So we need to find out the ratio of wavelength of the first line of Lyman series and first line of Balmer series. So for Lyman series, N1 is 1, N2 is 2. For Balmer series, N1 is 2, N2 is 3. So 1 by lambda Lyman will be R, 1 by 1 square minus 1 by 2 square will be R, 1 minus 1 by 4 will be 3R by 4. So 1 by lambda L is 3R by 4, or lambda L is 4 by 3R. Then for Balmer series, 1 by lambda B is R, 1 by 2 square minus 1 by 3 square. So 1 by 4 minus 1 by 9. This is 36. 9 minus 4. So it is 5R by 36. So lambda B is 36 by 5R. So if you make the ratio, so lambda L divided by lambda B, it will be 4 by 3R into 5R by 36. So R gets cancelled out. 4, 9, it will be 5 by 27. So lambda L is to lambda B will be 5 is to 27. So the correct answer is option B, 5 is to 27. So these two questions are pretty much similar, but the approach was different. Question number 9 then. As per Bohr's model, the minimum energy in electron volt required to completely remove an electron from the fast excited state of the doubly ionized lithium atom, that is Z equal to 3 is. So we know the options are option A 1.51 eV, option B 13.6 eV, option C 30.6 eV, and option D 122.4 eV. So we know for En direct proportional to n square. So here we need to completely remove an electron from the fast excited state of doubly ionized lithium atom. So here it is fast excited state, fast excited state. So what will be the value of n, and then doubly ionized lithium atom, that is lithium 2 plus. Then what will be the value of Z? So for lithium Z is 3, and for fast excited state we know n equal to 1 is for ground state. Then for fast excited state it will be n equal to 2. So n will be 2. So n is 2, Z is 3. Then what is En? We know E is minus 1.8 m z square E4 by n square h square epsilon 0 square. So it is minus 13.6 into z square by n square ev. So E is, so for lithium, so minus 13.6 into z square, z is 3, 3 square divided by n square, n is 2, 2 square. So minus 13.6 into 9 by 4. So if you calculate it, minus 13.6 to 9.9 by 4, it will be minus 30.6 electron volt. So this is the energy of the electron. So what is the required energy? So the required energy will be plus 30.6 eV. So correct option is option C, 30.6 eV. I hope this is clear to everyone. Now we'll move to question number 10. Question number 10 says, which of the following statements is true regarding Bohr's model of hydrogen atom? Options are option A, orbiting speed of electron increases as it shifts to higher orbits away from the nucleus. Option B, radius of allowed orbits of electrons are proportional to the principal quantum number. Option C, frequency with which electrons revolve in orbits around the nucleus is inversely proportional to the principal quantum number. Or option D, energy of the electron bound to the nucleus increases as it shifts to outer orbits. So these are the four options, and we need to find out the statement which is true. So each statement requires some analysis to find out whether it's true or false. So I'll give you a few minutes, and then after a few minutes we will discuss. So question says which of the following statement is true. Now let's analyze the first sentence. So it says orbiting speed of electron increases as it shifts to higher orbits away from the nucleus. So now what is the expression for V? V is Z square by 2 epsilon 0 NH. This is the expression for V. So the orbiting speed of electron increases as it shifts to higher orbit. So Vn is inverse proportional to n. So when n increases, V decreases. So the first option is not true because when the electron shifts to higher orbits, its speed decreases. It's here it is written that it is increases. So the first option is not true. Now coming to second option, option B. Radius of allowed orbits of electrons are proportional to the principal quantum number. So we know R. R is right proportional to n square. We had already discussed. So R is proportional to n square. It is not proportional to n. So again this is not correct. Frequency with which electrons revolve in orbits around the nucleus is inversely proportional to the principal quantum number. So frequency with the electron revolve. So what is the energy value? So E is m z square e fourth by n square h square epsilon 0 square minus 1 by 8. So E is proportional to 1 by n square. So now E is h nu. So h nu is proportional to 1 by n square. So nu also is proportional to 1 by n square. But here it is say it is inversely proportional to principal quantum number. So it is inversely proportional to the square of principal quantum number. So again this is not correct. Then option D. So what option D says? Option D says energy of the electron bound to the nucleus increases as it shifts to outer orbits. So we know E is proportional to 1 by n square. So but E is negative. So as n increases, E decreases, but it decreases negatively. So we can say E increases because we know E1 is minus 13.6 electron volt, E2 is minus 13.6 divided by 4, which is how much? Minus 13.6 divided by 4 is 3.4. So minus 3.4 ev. So now you see minus 13.6 is lesser than minus 3.4. So as n increases, the energy of the electron bound to the nucleus increases. But since it is negative, it may look like the energy value is decreasing. The modulus of energy decreases, but since the energy is negative, so energy is increases. So the correct option is option D. With increase in energy of the with increase in the outer orbits, with increase the value of n, the energy of the electron bound to the nucleus increases. So I hope this is clear to you. Now you have to move, now we move to question number 11. It says the ratio of wavelengths of the radiations emitted when the electron jumps from third to the second orbit of hydrogen atom to that of the electron jump from fifth to the third orbit of the hydrogen atom will be. So it is again similar. So 1 by lambda 1 will be R 1 by 2 square minus 1 by 3 square. So it will be 5 R by 36, or lambda 1 is 36 by 5 R. Similarly, lambda 2, it is R from fifth to third orbit. So 1 by 3 square minus 1 by 5 square. So it is R 1 by 9 minus 1 by 25. So 1 by lambda 2 is R 925, so it will be 225 minus 9, so it will be 16R divided by 225, or lambda 2 is 225 divided by 16R. So what is the ratio? So lambda 5 to 3 divided by lambda 3 to 2, ratio will be 225 divided by 16R into 5R divided by 36. So if you calculate, it will come out to be 1125 divided by 576. So the correct option is option A, 576 is to 1125. Now to question number 12, which is the last question of today's interaction session. It says the first member of the Paschen series in hydrogen spectrum is of wavelength 18,800 angstrom. The shortest wavelength of the Paschen series is. So what will be the shortest wavelength? Options are option A 1215 angstrom, option B 6560 angstrom, option C 8225 angstrom, or option D 12850 angstrom. Now what is the value of n for first member of Paschen series? So for Paschen series, first member Lyman is n equal to 1, Balmer 2, and Paschen 3. So n equals to 3, n1 equal to 3, and n2 is 4. This is for first member. Then for second member, n1 equal to 3, n2 equal to 5, like that. But what will be the shortest wavelength? So the shortest wavelength, so wavelength shortest, that implies energy is maximum. So it corresponds to n1 equal to 3 and n2 equals to infinite. So this transition which occurs from n2 equals to infinite to n1 equal to 3 is correspond to the shortest wavelength of the Paschen series. So first we will find the value of R, and then we will put that value to calculate the wavelength of the shortest series. So 1 by lambda is R, 1 by 9 minus 1 by 16, that is 1 by 3 square minus 1 by 4 square. It will be 144 7. So 7, so lambda 1 is 144 divided by 7R. Now for lambda L, that is the last member or the shortest wavelength, what will be 1 by lambda L? It will be R 1 by 9 minus 1 by infinite, that is R by 9. So what is the value of R? R is 7 lambda 1 divided by 144. So if you put the value, so what will be lambda 2? 9 by R, that is 9 divided by R is 7 lambda 1 by 144. So 7 lambda 1 into 7 into 144. So 9 into 144 divided by 7 lambda 1. So 9 into 144 divided by 7 into 18,800. So if you calculate, it will come out to be 8,225 Armstrong. So the correct option will be option C, 18,225 Armstrong. So the first member of the Paschen series, we know n equal to 3, n equal to 4, and the shortest member will be n equal to 3 to n equal to infinity, because then the energy will be maximum. So maximum energy corresponds to minimum wavelength, that is the shortest wavelength. So first we use the formula m1 minus n1 square minus 1 by n2 square to calculate the value of lambda 1, that is the first member. Then by putting the value of R in terms of lambda 1, we calculated the wavelength of the second member. I hope this is clear to everyone. With this, we come to the end of today's interaction session. I hope the questions that I have solved in this interaction session will definitely help you in solving your problems of the course assignment as well as for your exams. With this, uh, I come to the end of today's interaction session. That's it from my side. Thank you. You have any question? I can see SJ Margarate, you have joined. Do you have any doubts? Okay, if not, we can end the interaction session. Thank you all for attending. I will be anyway. I will be uploading this interaction session on YouTube, and the link it will be shared by NPTEL to you. Thank you.